the other points you need to keep it in mind while doing the disconnection. The most electron withdrawing group to be disconnected first, that is to be added last in the synthesis. Whichever you have disconnected first will come into the picture during the synthesis at the last during the synthesis part. So let us assume you have a target molecule that is 1 tertiary butyl, 2 methoxy, 4 methyl, the 4-methyl, 3,5-dinitrobenzene. So let us assume this is your target molecule. So in this case, do we have any electron withdrawing groups? So see this structure and let me know which end all group will act as electron donating and which groups will act as a electron withdrawing group. So what about your nitro group?
Withdrawing.
So nitro is withdrawing. Okay, so how many nitro group is present?
2.
2 nitro group. What about this methyl?
Electron donating.
Okay, and yeah, and what about this tertiary butyl? Methyl is donating, then tertiary butyl should also be donating, right? Yeah, because of plus I effect.
Methyl,
Yeah, so it's a plus I effect. So in this case too, plus I effect one can expect. And what about this methoxy? Methoxy?
Donating.
Donating
yes.
group.
So this is also donating. Okay. So if you look into this target molecule, so how many donating sites are present? 1, 2, and this is 3. 3 donating and 2 electron withdrawing group. So nitro will act as electron withdrawing and the rest 3 groups will act as an electron donating site. So as per this rule, the electron withdrawing group to be disconnected first. So now, which is the electron withdrawing group? So electron withdrawing group is NO2. You need to try to do the disconnection, particularly at the CN junction here, as well as simultaneously over here. After the first disconnection, you will get this synthetic equivalent. That is 1 tertiary butyl, 2 methoxy, 4 methyl benzene. Because as per this statement, you need to disconnect the electron withdrawing group, and after the disconnection of electron withdrawing groups, then you will get this kind of synthetic equivalent. Then question comes is, so now you have a 3 electron donating group, which needs to be disconnected. So in this fashion, we have disconnected over here. So why not over particularly CC of this or particularly CC of this particular function? Why needs to disconnect this tertiary butyl? Any reason for this? What will happen instead of doing the disconnection if you try to do the CO disconnection or CC disconnection?
Tertiary carbocation more stable.
Tertiary carbocation is more stable. Okay, fine. If it is more stable, then so you need to keep it in mind. What will be your last fragmentation? That is starting material you will get after the disconnection. Let us assume instead of disconnecting this, try to do the disconnection of CO. Can we do first thing is CO disconnection of COCH3? Then what will be your synthetic equivalents? One possibility is negative charge over here, then you protonation, you will get this particular system, and positive charge over the oxygen. But positive charge over the oxygen is not the good reagent, right? Oxygen prefers to carry a positive charge. So the possibility is either you need to assign this positive sign over here and negative sign over here. And if it is negative sign over, then you will get protonation, either methanol or sodium ethoxide or sodium methoxide. But over here, then positive charge means you need to use any corresponding halides or bromides. So if it is halides is already present, then you have a nucleophile of NaOCH3 Na plus and OCH3 minus. In this case, the nucleophilic substitution over the benzene, is it feasible? Because this is electron rich site, right? So the benzene system prefers electrophilic substitution reaction or nucleophilic substitution reaction. Benzene prefers electrophilic substitution reaction or nucleophilic substitution reaction.
Electro.
Yeah, so most of them is electrophilic substitution reaction because this system is electron rich system, right? So electrophilic substitution reaction is always preferred. So if it prefers to proceed via these, so even though you have a nucleophile and the CX system, but problem is the nucleophilic substitution reaction, particularly over this kind of system, is highly difficult. It needs to provide extra energy, so in drastic reaction condition. That's why those kind of reactions needs to be avoided during the synthesis. So ruled out. So disconnection particularly at this. So and then if you try to do the disconnection CCH3, then of course it is possible, but you won't get the simpler molecular system because this is donating and this is donating. So of course, whichever is having the donating ability, so which it will decides your incoming electrophiles to attack over the benzene system. So instead of going over here, our aim is to get the simpler starting material. That's why the bulky molecule in this particular system is tertiary butyl. So tertiary butyl you need to disconnect to get the simpler system. So simpler system is 1-methoxy 3-methyl benzene. You will get it after the disconnection of tertiary butyl carbon and the carbon of benzene. And always you need to keep it in that after the disconnection, whatever the synthetic equivalent you will get, you need to keep it in mind which functional group is present or substituent which is present over the benzene system. Whether these two will act as a ortho-para director or meta director, you should always know. So whenever you have in donating groups, that is always ortho-para director. As and when you have an electron withdrawing group, then it will act as a meta director. In this case, both are donating group, it is ortho-para director. So coming to the synthesis of that, so take this 1-methoxy 3-methyl benzene as a starting material, and how to construct the next step is you need to use tertiary butyl bromide, use this AlCl3, so Friedel-Crafts alkylation. You will get particularly this electrophile will attack over this particular site because electron donating group of this ability is more over this, and it helps to redirect the incoming electrophile to the ortho site. And you may ask why it won't attack over this ortho site, why specifically at this particular site. Is there any reason? Both are ortho with respect to this, both are ortho, and this will be the parasite with respect to this. Why this electrophile preferably attacks at the ortho of this particular site, not the ortho of over here? Any reason?
Steric hindrance.
Huh?
Steric hindrance.
Yes, steric hindrance. Let us assume this electrophile. So the electrophile should be, it's a bulkier system, right? Tertiary butyl cation. Tertiary butyl cation won't approach this particular site in this fashion because it is also bulky and there are sterically hindering groups is already present. So even though if you have a positive charge electrophile, E plus will come, it won't prefers to attack particularly in this direction because the steric hindrance experienced by this electrophile with respect to already existing substituent. Instead, the open space is this particular site, and ortho is of course it's an electrophilic substitution site. And tertiary butyl cation prefers to attack over here rather than over the parasite, because in this case too, you need to consider the electron donating ability. This is also electron donating. The more electron rich sites are ortho with respect to these two, if you combine it, ortho sites are more electron rich over this parasite. Only if you're considering this is the parasite. With respect to this is the parasite. So with respect to this orthosite and with respect to this parasite are electron rich. So that's why these two sites prefers to be more electron density over the particular this site. That's why you need to first give the priority. You need to look into these two sites whether the electrophilic substitution is possible, because this is slightly ruled out because of steric hindrance and it cannot easily approach this particular site. And next is the first priority you need to give it for the open space. So there is no steric hindrance causing group, which is already present over here. If it is there, then this is also slightly blocked. You may get the less conversion yield during the reaction. As there is no substituent present, particularly is this site, it prefers to attack at the ortho with respect to the methoxy. Okay, so after this step, then next comes is you have a two sites for the electrophilic substitution reaction. Nitration reaction. You need to use H2SO4 HNO3. So H2SO4 HNO3 is a nitrating mixture, nitronium ion. You will get electrophil. So electrophilic substitution reaction, of course. Then comes is, as we are using excess of HNO3 and H2SO4 mixture, you need to do the electrophilic substitution at the ortho. With respect to this now, because this is an first priority. So over any of this donating ability. So these two are electron-rich sites for the incoming electrophile. That's why NO2 electrophilic substitution occurs at this particular two sites. Ultimately, you will get the target molecule. So this was the target molecule we were expecting. And so in order to get this from the starting material of 1-methoxy 3-methyl benzene, you need to use two reactants. One is first step. In the first step, you need to use tertiary butyl bromide and AlCl3. And the next step, HNO3 H2SO4 mixture, that is nitrating mixture. So ultimately, you will get this target molecule.